Hello, I'm Yehan Liu. Welcome to my Lab 1 report about constant velocity. First, the introduction part. The purpose of the lab is to explore the concept of constant velocity by applying fundamental physics principles to real-world observations. I need to analyze the motion of an object and use Newton's second law to create a computational model, comparing it with the experimental data. And the fundamental physics principle used here is definitely Newton's second law, also known as the law of force and acceleration, states that the change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. Mathematically, it can be expressed as this also. Okay, then also some really important equations involved here are first, position update formula, which can help you predict the next position of the object based on its current position and velocity. And also momentum update formula can describe how the object's momentum changes under the influence of net force. And also by using velocity update formula, we can calculate the updated velocity of the object using its momentum. Then about the model evolved here, first is the experimental model, which is real-world observation. The motion of the object was captured and analyzed using tracker software, extracting its position and velocity over time. So this is my video for the motion. And then I used the computational model. It is created using the assumption that no net force acts on the object, allowing it to maintain a constant velocity. Then here is the preview of the result. It can be seen that the two plots are almost coincident at the beginning, and as time goes by, the observed plot slowly falls below the predicted plot. That is due to the gradual slowing down of the object due to friction and air resistance. Then about the experiment, the system is the cylindrical marker pen I used, and the surroundings are friction, gravity, and applied force by the person rolling the system. And about the initial conditions, I just assumed the system mass is 1 kilograms because it doesn't really affect the result. And for the system position, I set it to be, the initial condition, I made it to be 0, 0, 0 because I put the origin on the starting point. And the system velocity, according to the analysis of tracker, at first is 0.214. And the starting time, I set it to be 0.628. And the delta time, which is the size of each timestamp by the tracker, is 0.033 seconds. So the assumptions we made here is air resistance and friction were assumed to be negligible, but mainly for the computational model because we can't really get rid of those air resistance and friction. Then here's how I use tracker to analyze the video I recorded of the marker pen moving. So here is the plot of the magnitude of position versus time. You can see it's almost linear. So then it's a computational model. I used GlowScript to make the code. And let's just see the data here. So I just applied the initial conditions I assumed here. Like for initial velocity is 0.214 here, starting time 0.628, and the delta time is 0.033. And also see here the final time is 1.428. And for others, I just set the Fnet to be 0 because we assume here there's no air resistance or friction, so the net force should be 0. Then these two are the plots I got from the code. So first plot, you can see the position versus time. So it's a perfect upward line. And for the velocity versus time, the velocity remains constant. Then let's see the results of the lab. The plot looks great because we can see the two line stays almost coincident. And only the observed position line got a little bit lower in the last part. That's because of air resistance and friction. Also, there are two possible errors for the lab. First one is human error, is that when I roll the marker pen, it does not move straight and slightly moves to the left or right. This might reduce the accuracy of the experimental data. And second one is the accuracy error, is that there could be some inaccuracies when tracking the marker pen when using tracker. It's because I actually tracked the pen manually using my mouse, and it probably is not that accurate. Then here's my answer about the follow-up questions. First one, what if? How my results would change if I flip the axis. So the marker in my video is actually moving to the left, so the actual pen position value should be negative. But for ease of plotting, I'm using magnitude of position and not adding the direction factor. So if direction is factored in, the results of my experiment should be a mirror image of what it is now, as shown below, without the magnitude changing. Simply put, a change in direction will only change the positive or negative of the slope of the image, not the magnitude. Then the second question, what does it mean? Is it possible for me to say how many pushes and pulls, how many forces are added together to give zero net force in the case that I observed? And my answer is as follows. Since the marker is subjected to many simultaneous resistance forces, like friction and air resistance, I can't say for sure how many push and pull forces would have to be added together to make the net force zero. However, I can say that at least two forces, push and pull in opposite directions, are required to make the net force zero. Thank you for listening.